Recording is re-rolling for part 4 today. All right, so you guys just did this lab. We got all the graphs for all these relationships. So all these variables that we were juggling, remember we were controlling a few at a time, and then just independent, dependent, and then came up with lots of individual relationships that you guys have graphed. Okay. Now what I'm going to do is there's a green poster hanging on my wall that you guys see over the door right there. It looks like this. Okay. These three kinematic equations tie together all these variables that you guys could work with. X is like displacement or distance, like how far it's gone. T is how much time it's been going for. Okay, now you guys see some subscripts on these different V's. You guys might know this. What do you think V naught represents? Initial velocity. And guys, if you were releasing a car from rest, what was your initial velocity every single time? Yeah, it happened to be 0. Anything that starts from rest, then V naught is going to be 0, right? What do you think VF stands for? Like final velocity? Maybe like after the car's been rolling for some interval, like the end of the interval. Ooh, do you think all these equations are set up like beginning of the interval and end of the interval? So it's really like 2 points, right? Initial, final, okay, something like that. Initial, final. Okay, and then there's this A. What does A stand for? Acceleration, which is like the rate that it's picking up velocity. Okay, you guys got that? Okay, all right. So let's okay, I'm gonna go drive these for you guys. Give you guys some notes here. Okay, so you guys got your traditional notes out. We get an idea. Okay. Let's just start with a non-accelerating situation. Suppose that you're, well, you guys could probably say this, right? Velocity is displacement over time. Probably say something like that, right? Or you might say speed is distance over time, right? Now those are slightly different things. So here, give you guys an example. Suppose you're just going straight on I-95, just straight north, just in a straight line, right? Can I rearrange it like this? This equals speed times time. Okay. So this is for 0 acceleration. Those are two perspectives on the same thing, right? Okay, so, okay. Suppose that you see a sign. It says Jacksonville is 180 miles away, and you're going 60 miles an hour. 180 miles away, 60 miles an hour. How long is it going to take you to get there? Like 3 hours, right? Because 60 miles an hour times 3 hours bring them to 180 miles. Okay, okay, yeah. Okay, so you guys got that. So go to example. Okay, or if you had some distance divided by how much time, that could give you the speed. Okay, now what if you did so? What if you take a just think ahead. You said take a ball, throw it straight up, and it comes like down again, something like that. Okay. Do you guys think that the displacement would be the difference between starting point and ending point? Right. Now I'm talking about displacement, not distance, right? Because distance is you have to add everything up, right? And all these equations are eventually going to, you care more about displacement, right? So if you're ever wondering like, which one is it, or it's ambiguous, or they'd be two different things, you care about displacement, not distance. Okay. Okay. So we got that. That all looks fine and good. Now this is, as long as you're ever going constant velocity, you could just do that and you're done. That's the only equation that matters. Now constant velocity, 0 acceleration is the same thing. So 0 acceleration, constant velocity. Let's peek ahead a little bit. We're eventually working towards these, right? Now, if your acceleration is 0, let's just see how these equations would each play out. If you plug in 0 right there for that A, for 0, like constant velocity, doesn't that just boil down to that? Hey, that's the same thing. Displacement equals velocity times time. And initial velocity would just be velocity because it wouldn't be changing. Does that make sense? Okay. What about the next one? If this acceleration is 0, hey, final velocity is initial velocity because you're not changing your velocity, right? I see that. And what if this acceleration is 0? Hey, same thing. You just square root both sides, and it looks like the same as the last one. All right. So you can see how what we're working towards. At least it's consistent with 0 acceleration situations, right? Okay. Now, what if you are accelerating just like that entire lab you guys did had accelerating cars because the cars were speeding up as they were, well, they released from rest and they started moving, so they better speeding up, right? All right. So what I'm going to do here is okay, let's do the velocity versus time graph that you guys had. Velocity versus time. Okay. Now, I think that was the third experiment. Somebody said this one. I told you guys this is going to be a really important graph you're going to see all over the place, and here I'm using it to start derive these. Let's call this meters per second, and let's call this seconds. Okay. And you guys just got the data for this because you guys just did the lab. Remember, all your points pretty well lined up in a straight line. like that. Isn't it? So direct relationship. Okay. So could you say that velocity is proportional to however much time has passed? Okay. And what's the slope of this line again? Acceleration. And here's the definition of acceleration. Rate change of velocity per time interval. Right? Delta t, I'm going to call time interval. But delta v is like v final minus v initial. Okay, so sometimes it's both ways. Okay. So yeah, there's like the definition of acceleration, right? The rate change of velocity. Okay, guys got that? Okay. Right. So I'm going to go back to this proportionality. I'm going to make this an equation. Can I say that the velocity picked up to is equal to acceleration times time? That's like y equals mx, right? Right. And let me go and because the way I drew this graph, see how I'm starting from zero velocity? What if you did not start from zero velocity? What if you started counting like right here? And so your graph actually like had a y-intercept. Wouldn't it look like that? And then would it just be y, or whatever velocity you pick up to is still equal to acceleration times time, but it's just plus the initial velocity, kind of like a y-intercept. Wouldn't that be true? Okay. So what I'm trying to get at is I'm going to redraw this graph just with a different y-intercept. Okay. So here's a more general version of this. Velocity in meters per second versus time in seconds. Okay. And this, what should I label this point again? This y-intercept? V naught. Oh yeah. There you go. Because that would be the initial velocity. Here's 0 time, then time tick, 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 ticks along. Okay. Okay. Now, you guys know that the slope of this is acceleration. You guys told me that, okay, which is in here, acceleration, or the slope of a line is not rise over run. So it'd be meters per second per passing second. And what's that again? What's meters per second per second? Meters per second squared. Okay. So see how that unit attaches to that variable? Okay. All right. But there's another piece of data you can get out of this graph. So you can see here's what we got so far. You know, you can look at any particular time, you can know exactly how fast it's going, right? Just the coordinate of the graph. You can use this data to get the acceleration by taking the slope, right? The rate change. So you get velocities, you can get accelerations, but there's another piece of data you can get from this graph. Okay. How about this? You guys see like a trapezoid shape like that? You guys see a trapezoid? Okay. Hey, I wonder what shape this area has. Or sorry, what I said that wrong. What unit this area has? Area, is that something like base times height? If it was a rectangle, it would be base times height exactly, wouldn't it? Suppose I split this into like a rectangle and a triangle, right? Hey, this base times this height. Guys, what is this meters per second multiplied by what's the unit for the base of this rectangle?
Seconds.
Seconds. What is meters per second multiplied by seconds? Meters, right? Displacement. You got it. So doesn't the area of this shape under anything under the v versus t curve represents what variable? Displacement. In this case, measured in meters, right? You guys got that? Okay. Hey, I wonder if we could take these two shapes, this rectangle plus this triangle, and put it all together into one giant equation. Ooh, let's do it. I'm gonna call this just some generic time t. It could be however many seconds, right? So what's the area of this hashed-in rectangle? Yeah, v naught times t. So this is v naught times t. Okay. In fact, if you're just going constant velocity at I-95, however far you go, x equals v naught times t. That's it. X equals vt. Okay. But how about this triangle? Oh yeah. What you think?
Is it delta v over t times 1/2?
There you go. Yeah, so 1/2 base height, where right the base is t, and the height, you're right, would be final minus initial velocity. I could label final velocity up here too, right? Just feel like some v set up. Right? Yeah, you're right. That is one way to do it. Now I'm gonna do something a little trickier too. Do you guys think I should have started with the next equation, but you guys will get this anyway. Okay. If you just focus on that triangle, okay, the speed you pick up to final velocity, isn't that just starting at 0? It wouldn't just be a slope times time, like acceleration times time. Okay. So this right here is acceleration times time, right? This base is some time t. So area of a triangle, that area right there, is that 1/2 times the base times the height of the triangle, right? Okay. Okay. And ooh, that's the same time, isn't it? Can I call that 1/2 AT squared? Is that okay? Okay. Okay. So let's take this piece. Anything that starts from rest. Okay. The fact that your car is just rolling down like from rest, like the area of this triangle is 1/2 AT squared. Okay. But if it starts not from rest, then couldn't you just add this here rectangle to it? So put it all together. Doesn't it look like displacement equals this rectangle plus this triangle? Is that true? Okay. And that is this here top kinematic equation. Beyond t plus half at squared. Boom, there you go. Okay. And those of you who were measuring displacement versus time, and you guys got a parabolic relationship, and so then you did x versus t squared, right? You guys remember doing x versus t squared? Now, your car started from rest, so what was this B naught again for your car? 0 because it started from rest. So you guys just had this, right? And I told you that the slope of x versus t squared was half the acceleration. Ah, that's why. So suppose you got like, I just make up a number. Suppose you got like 0.25. Well, that's half the acceleration. So if you double that, 0.50, and then either meters per second squared or centimeters per second squared. Okay. You guys got it? Yeah, and AP could totally ask that. Okay, so that's that one. Actually, I should have started with the second equation because we kind of had to do this to get this. That's this part right here, isn't it? Okay. So let me go back to, actually, it's just pure the equation of this line, isn't it? Okay. Isn't it like y equals mx? Okay. So the equation of this line is the speed you pick up to, calls df, is equal to mx plus b. I know the slope is acceleration, however much time has passed, that's like the independent variable. And then your y-intercept is like the plus b naught. Isn't that y equals mx plus b? Okay. Now all I'm going to do just per convention is just take that intercept, shift it to the front, and then that looks like the speed it picks up, or the velocity it picks up to is the initial velocity plus the acceleration times time. There's your second equation. Okay. You guys get the part? Now, since your car started from rest, that V naught was 0 for you guys. Get started from rest. Yeah, go.
Will you be given like this the velocity versus time graph? Like, will you be given the graph and be told to find displacement?
Yeah, that could be a really good question. Yeah, there's a really good chance. I'd be shocked if you did not see a velocity versus time graph on the AP exam. Yeah, and it could ask a bunch of questions about it.
So if you were to get the graph on the exam, would you have to go through all of the algebra, or could you just do a shortcut to the answer?
There's lots of different ways they can ask the question. They might give you a table of data and say like find what's the acceleration of the car. Yeah, or they might actually give you the graph and say like how far does the car go, and so you have to find like the area underneath it.
If you were to use you had the graph and then you had the equation to find so if you have the equation for your graph and use the integral to find your displacement, would you get points marked off for that?
If they want you to find displacement.
Yeah. Would you get points marked off because it's a shortcut? Because you're not using the algebra.
Oh, okay. Yeah, so I'm just taking you guys through the algebra and the graphs just to like derive these equations. I mean, yeah, if you solve it with an integral and then also get the answer, then that's fine as long as you get to the right answer. Okay. Yeah. So, and what Marcus is talking about is how many guys are in calculus? How many guys are in calculus? Okay. Okay, so there's a calculus relationship among floating around a bunch of these graphs. And you guys remember I told you guys calculus is about rates of change, right? So the rate change of velocity is called acceleration. So when you guys are finding like derivatives, you guys are finding instantaneous rates of change. If you guys found like the derivative of v versus t, that would represent acceleration. And then if you go the other way, if you want to find out what displacement is, which is the area of this trapezoid, that process is called integration, and you'll get to that like the second half of calculus, right? Now, so calculus, they give you like certain procedures, like how to manipulate formulas. But then when you get to that part in the textbook, look back at your physics notes and you realize that, hey, everything lines up. Right? So rate change of velocity is acceleration, but if you add up, if you accumulate the velocity with time, you get displacement. Okay. Okay, so guys good so far? Okay. Now, what about what about this last guy? Because we knocked out these two. So you guys good with these two? Okay. Now I think if you sit down and study these a bit, you can make intuitive sense of these top two. Yeah, and I gave you guys the notes for it so far. Right. This third one, here, which variable do you not see in that listed in that third one? Time, right? So there's certain tricks to figure out like which equation is going to help you answer which question most quickly. If you are not told how much time, say a car's been rolling for, a ball's been falling for, and you're also not asked about it, there's a really good chance that it involves the third one. For example, if you're told the height of a cliff on what planet, and you want to know how fast it's crashing into the ground, then this will get you there the fastest. So like the top two each have time mentioned in them, right? Now, obviously, all five variables, v naught, vf, x, a, and t are going on with all three equations, but they're not mentioned in all three equations, right? They all have acceleration, but only the top two mention time, the bottom one doesn't mention time. Okay. So what if you had a situation like that? Like you throw a ball down from the top of a cliff. Oh, that's initial velocity. You want to know how fast it crash landing. You know the planet you're on, which has to do with this acceleration, like how much is gravity pulling. You know the height of the cliff, so you're trying to solve for the crash speed. Okay. Well, you could go through the top two equations, but it'd be a system of equations, right? You have to solve for t, like how long was it falling for, and then take that, and then okay, but then that could get kind of tricky. So if you take the top two as a system of equations, then you can get the bottom one. So you can check this too. So turns out final velocity squared equals the initial velocity squared plus 2ax. Now, on the AP exam, you guys are allowed to use the AP equations, which is this page right here. Okay, you guys are allowed to reference it. And these top two equations are, they are the ones I've been going over. The AP writes them slightly differently. AP writes x in terms of location. I've been writing x in terms of displacement. Displacement is like how far you've moved from the initial place. Okay. So AP writes them a little bit differently. AP writes final position is equal to initial position plus, and then just continues like that, right? Okay, but basically it's top three. I do recommend that you do memorize those equations though. And so, just take some time, maybe make some flashcards, maybe just use these equations a bunch. Okay. Okay. All right, so you guys good with those equations? Okay. All right. So next set of notes. Let's go to the edge of a cliff and drop a ball. So yeah. Yeah, got it. So I'm gonna drop a ball from the edge of a cliff. Okay. Now, if I'm dropping the ball from the edge of the cliff, okay, so linear motion, the ball is just going straight down. Okay. I do need to define a direction that's the positive direction. So I'm going to define down as the positive direction. Now, you don't have to. You could define upwards as positive and down as negative. There's no problem with that. But I'm just going to do it this way, then all the numbers are just going to be positive. Edge of the cliff is 0.0, and it just moves into positive territory as it's falling down, down, down. Okay. Let's make 3 graphs here. So 3 sets of axes. So, okay, so start typing your last name. Here. Start typing your last name and then destination. That's what worked out. Then I think you can scan yourself out. All right, let's go displacement versus time. This is gonna be meters and seconds. Let's go velocity versus time. This is meters per second and seconds. Notice I'm labeling all the axes, variable unit, variable unit. And then we'll go acceleration, meters per second squared versus time in seconds. Okay. Okay. Good so far. Get this stuff out right here. Clean background. All right. So if you drop a ball from the edge of a cliff, now if you drop the ball, then here's what I'm gonna do, and I usually do this way: is start with the middle graph, v versus t, and I'm gonna branch out from there. Okay, because kind of like what Marcus was referring to. If you take the rate change of velocity, that tells you acceleration. If you integrate velocity versus time, that takes you to position. So they're each a step away from velocity. So I'm gonna start with velocity versus time, right, and then we'll work out from there. Okay. So if you drop the ball, then at time 0, how fast was it moving? 0 meters per second. Okay. Now, if you're ever solving a problem, sometimes there are numbers that are embedded in words like that. So if you drop something or release from rest, you'd have to say, initial velocity is 0 meters per second. If your eyes are just starting around looking for numbers, they're not going to explicitly type the number 0, but okay, drop the ball. That means initial velocity 0. You'll make a note. V naught equals 0 meters per second. Okay, that's what that term drop means. Right? Okay. What do you guys think the rest of that little graph is going to look like?
Increase someone.
Okay, and the answer is already on your lab paper. Right? Oh, I forgot to make a table here. I'll make a table separate from this too. Just gonna do. Okay. This is all okay. This fits on that screen. Fits on the screen. I'm so sorry, guys. Gotta do. Okay, let's do a 4-column table here. Okay, sorry. So how much time has passed in seconds? Let's go acceleration meters per second squared. Let's go velocity in meters per second. Let's go displacement in meters. Okay, so let's let the ball fall 0, 1, 2, 3, 4, 5 seconds. And let's say after 5 seconds, it's about to crash into the ground. I was gonna draw you a picture too. Here, we put a picture over here. So, because I want you guys to see what this looks like. Here's my cliff. Here's the ground down here. Okay. So I'm gonna reach over the edge, drop a ball. Okay. And let's say you take a snapshot every second. Tick, 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 tick. You think it would look something kind of like this? Tick, 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 tick. So times 0, 1, 2, 3, 4, 5. Look kind of like that. Hey, see how the ball's like spreading out every single successive second? Right? Okay. Now, do you guys think that the rate that gravity let's go with this middle column here. Okay. So after 1 second, how fast is it? Oh, you guys have to know what gravity is. Okay. Does anybody know the free fall on Earth if you're going straight vertical? Because this scenario, dropping the ball off the cliff, is a lot like that toy car rolling down the incline, except that it's going to have the acceleration is going to be a lot more. Yeah, go ahead, sign out. Okay. Right, so your guys' incline like slows down gravity, right? Like if you had a perfectly horizontal incline, it would be 0 acceleration. If it's perfectly vertical, it'd be exactly free fall. Okay? So what is the free fall on Earth? I'll call it G. Yeah, 9.8 meters per second per passing second, called 9.8 meters per second squared. Now, I'm going to round that number to 10 meters per second squared. Okay? And AP oftentimes says the same thing. In fact, whether you use one or the other, 9.8 or 10 meters per second squared, you'll get all the AP will take either one of those. The multiple choice will be close enough to do either way. Right? It's kind of like if something's $1 versus 98 cents, like almost the same number. Right? Okay, so at time 0, there is 0 velocity. That be true? After 1 second, how fast is it picked up to? Well, let's try this out. So starting from rest, so let's just bump this guy goes to 0, right? 10 meters per second squared times 1 second is what? 10 meters per second, right? Be 9.8. Right? We're gonna round a little bit. We're also ignoring air drag. Yes, we're ignoring air drag, right? After 2 seconds, so what's 10 meters per second squared times 2 seconds? 20 meters per second. After another second, how fast? 30 meters per second. Another second, how fast? 40 meters per second. Another second. 50 meters per second. If it's about to crash land, how fast is it crash landing? 50 meters per second. Ah, if you didn't see it before, I bet you guys see now how this is going to linearize, right? Every single second that passes, it gains 10 meters per second, right? Fix it. All right. Next thing, what is the slope of this curve represent again? Acceleration. Thank you. And is the slope changing anywhere, or is the slope the same all the way along? It's the same everywhere, right? So what do you think goes all the way down this column? Yep, there you go. So as soon as you release it, it starts accelerating at 10 meters per second per passing second. It's all the way down, isn't it? Right? Again, we're ignoring air drag. We're always going to ignore air drag in this class, unless it says to specifically, like explicitly to consider air drag. And then it's usually more of a conceptual thing, like, well, if there was air drag, then maybe it wouldn't like go as far or as fast or something like that. I've seen the air drag variable solved one time in a class past calculus 3 in college. And all right, so I survived that one. Okay, move on. What do you guys think acceleration versus time looks like? 10, 10, 10, 10, 10. Right? 10 meters per second squared. Okay. And that's for the Earth value G, 10 meters per second squared. Okay. It's always 10, no matter how long it's been falling for, as long as it's in a vacuum. It's picking up 10 meters per second every passing second. Hey, do you guys see how the points of A versus T, the coordinates of A versus T, are the same thing as the slope of V versus T? Okay. So there's a relationship here. Go here, here. This is the slope relationship. Okay. Now you could go back the other way too, because suppose you were going 1 second at 10 meters per second squared. Guys, what is the area of this rectangle? What is 1 times 10? Yeah, 10, and then yeah, you're right, meters per second, because meters per second squared times seconds would be back to meters per second. Hey, that's like the change in coordinate of this graph. You guys see that? Right. And what if you went like another second? Will this pick up another 10 meters per second? Ooh, which brings you up to 20 total meters per second, right? Hey, so what property of A versus T tells you B versus T? The areas. Yeah. You guys see that? Okay, so the rate change of velocity versus time tells you acceleration. And the area under A versus T leads you back to change of velocity. Right? You guys see that? Okay. And the calculus terms are, I bet some of you guys know the calculus terms. What's this called a calculus? Derivative. And what's this called a calculus? Integral. Okay, guys got that? Okay. Now that derivative integral relationship, do you think that same pair of relationships also applies to these top two? Turns out it does. Okay. Now, well, let's do the table first. Do the table and we'll go plot the numbers. Okay. Now, if you release from rest, this V naught just goes to 0, right? So this whole piece goes to 0. So is it just x equals 1/2 at squared? Okay, you guys got that? Okay, let's figure this out. We'll call the top of the cliff position 0. So 0 time hasn't fallen anywhere yet. Remember, we're calling down positive. Okay. So if it's been falling for 1 second, what happens when you plug in 1 for this time and 10 meters per second? So 1 second here and 10 meters per second squared here. What do you get for x? 5 meters. You do get 5 meters. You guys get that? Because 10 times 1 times 1/2. Right. Okay. How about if you plug in 2 seconds here at 10 meters per second squared? What do you get? 20 meters it's fallen. Right? Right. Now this 20 and this 20, totally different concepts, right? This is meters per second, this is meters. Right? It's kind of a coincidence they happen to be about the same number. What if it's been falling for 3 seconds? 45. So go to the edge of any very tall cliff on Earth, drop a ball for 3 seconds. How far is it falling? 45 meters. You guys get that? Okay. If you have a cliff that's so tall it's been falling for 4 seconds, how far is it falling? 80 meters. You guys see 80 meters? Okay. 1/2 times 10 times 4 squared, that's 80. Okay. And then what if you go to the edge of a cliff? You drop a ball and you count off. It takes 5 seconds to reach the hit the bottom. How tall is the cliff? 125 meters. Okay. 5 squared, 25 times 10 divided by 2. 125 meters. Okay. You guys get that? Right. Now this only works on Earth, right? Because 10 meters per second squared. Right. If you went to the moon or Mars, then well, right, numbers would change. Okay. Okay. You guys go to the table. Okay. Now if you plot the points, so at time 1, it's plot. Do you have time to plot this sort of? Yeah, I think I got this up. Enough time. Scale is to 125, right? 25, 50, 75, 100, 125. 125 meters right there. 2, 3, 4, 5. So 1 second, 5 meters. 2 seconds, 20 meters. 0 was a point also. Right, 345. It's right about there. 4 is 80. And 5, 125. Guys, what shape is that? That's a parabola. Okay. Now, if I hold my roller flush to the curve, what point of the parabola is this right here? Starts with a V. It's called the vertex. This would be the vertex here, right? As long as you're dropping the ball. Now, if you throw it, that's gonna go out of whack, right? But what is the here? If I hold my roller flush to the curve, what is the slope of the curve right at the vertex? 0, 0, right, 0, right. Then it starts to change, right? What do you guys think the slope of the curve is after 1 second? So many meters per second, right? Meters per second. Hey, that describes a velocity. What's the velocity at 1 second? 10 meters per second. What's the slope of the curve at 2 seconds? 20 meters per second? How about 3 seconds? 30 meters per second? How about 4 seconds? 40? What? How about 5 seconds? 50? Does it look like the slopes of each of those x versus t is describing the coordinate of v versus t? Slope. You guys get that? Okay. And finally, if you start adding up the area under v versus t, so suppose I like adding these areas up. Well, let's just because now we're getting pretty close to the bell right now. What unit does this area have? What is meters per second multiplied by seconds? Meters, which describes the displacement. Do you think that the cumulative area that you add up under v versus t describes x versus t? And look at that. Every second that you add, these trapezoids are getting bigger and bigger and bigger, aren't they? Okay. Area again, area. Right? Guess that? And of course, the calculus term for that is integration. All right. That is a pretty good pause point today. Guys, turn in your labs. I'll go through, give you guys points for those. You guys get great right here. If you need to staple it together, I got fresh staples right here. So turn your labs into the grade tray. Everybody's turn their labs into the grade tray. Yeah, okay. Do that.
Just fill your labs.
All right. That's a good pause point for today.